This program is called a ripple tank simulator. So a ripple tank is like a tank full of water that has a little mechanical oscillator going up and down, making harmonic water waves. So this computer program mimics, actually in a much more controllable way, what you would see in a ripple tank. So and I put the source in the middle. I'm filming with my smartphone because my screencasts, if I'm doing something CPU intensive, sometimes it seems to interfere with my ability to record a screencast. So I'm going to let the waves start, and you can see circular waves emanating out from the source. And you can see that as we get farther and farther from the source, the wavefront becomes less dark. So that corresponds to a diminished amplitude as you get farther away from the source. In 3 dimensions, that would correspond to our inverse square law for intensity, because the same energy is spread out over a larger and larger surface as you get farther away from the source. So the intensity diminishes in 3 dimensions as 1 over r squared, or in 2 dimensions as 1 over r. And then the amplitude goes like the square root of the intensity. So, well, you don't have to know that, but so in 3 dimensions the amplitude would diminish like 1 over r, and in 2 dimensions the amplitude would diminish like 1 over the square root of r. So we can look at a 3-dimensional view, and this makes it a little more clear, I think, that there's a big amplitude when the wavefront is just a short distance out from the source. And by the time the wavefront gets out here, you can see that the amplitude is a lot smaller, or a decent amount smaller. And again, the effect is less dramatic in 2 dimensions than it is in 3 dimensions. Now this is with a boundary that's sort of like an open field. So the waves, there's no reflection. So this is sort of like what would happen out in in the Penn Park, in a football field. So now if we add a border, we'll see reflections. And now this is more like indoor conditions. So you get reflections from every surface. This is sort of like if you were talking, singing, playing an instrument in a room with hard walls, and then you no longer see the strong dependence of intensity on position. It seems as if the wave energy has filled the room pretty uniformly, and we can look on the 3D view and see that indeed it seems as if the amplitude, or you could square the amplitude and call it the intensity, it looks as if the height of the waves, so basically the amplitude, is pretty much the same all over the room. So this is sort of the effect. You talk in a room with hard walls, a decent reverberation time, then the inverse square law for distance no longer really holds, because the sound fills the room in a pretty uniform way. Okay, now I have a custom setup here called WJA1, and this is showing reflection from a barrier. So this is similar to last week's sound waves reflecting from a wall. So it's kind of analogous to what I was doing with the wave machine, where I put one mass in the middle of the wave machine, and you could see that some of the wave was reflected, thereby staying in the source room, and some of the wave was transmitted into the destination room. So you can see that here. This blue line in the middle is kind of like a wall between, let's say, my room and my flatmate's room. And maybe I'm playing a musical instrument in my room, and you can see that some amount of the intensity gets through to my flatmate's room through the wall, but that it's significantly diminished going through the wall. Now I think I can show you that higher frequencies are easier to stop and lower frequencies are harder to stop. So let's see, so I can change the source frequency. If I go up to high frequency, we try that, and then I will clear the waves. I think we'll see a lot less wave getting through. Oh yeah, look at that. You basically see, well, you can see just a tiny little shadow getting through on the bottom, so that's pretty decent. So the high frequency waves um, don't, for a given barrier, the transmission is proportional to 1 over the frequency squared. So high frequency is transmitted much less than low frequency. So now let's go down to a very low frequency, and I think we should see that it's very hard with a barrier to stop low frequency waves. Here, let's see, let's go down to something like this and clear the waves. Okay, so I haven't tried this recently, but I think we're going to see that a decent fraction of the wave gets through into the adjacent room. Yeah, I think that's true. The way these waves are so large, it's sort of hard to see what's going on. We could try a slightly higher frequency. So I think at this intermediate frequency, yeah, so you can see that there's a wave getting through, but you can also see that it's quite a bit lower in amplitude. Let's see if the 3D view helps. I'm not sure. Okay, yes. So you can see that the amplitude over here is quite a bit smaller than the amplitude on this side. So I think that's probably a helpful view. Okay, let me go to a kind of more intermediate frequency. All right. So the next thing, I have a setup called WJ2, which is my middle initial is J, which is a double wall. So let's see how that works. Okay, here's a double wall. So I think we should see that some of the energy gets through into the middle, but then really very little gets through to the adjacent room. So I think, and I guess maybe the 3D view makes it even more, yeah. So you can see there's a little bit getting through into this kind of middle region, but then very little makes it to the opposite side. And then we can try this, well, it should be even more dramatic at high frequency. I guess we could try that. Clear the waves. And yeah, so that's not even that interesting because almost nothing makes it even into the intermediate region. Now, I think at lower frequency, the double wall does a much better job than the single wall. Let's see how that goes. And then the 3D view might help. Yeah, so I think you can see that the double wall does an okay job even at low frequency. Here, let me make it a frequency that's a little more visible. Okay, so actually, here's a frequent. Well, it's not. This at this particular frequency, the barrier just does an okay job, I guess. That's interesting. You can go a little bit lower in frequency. Okay, and then what are we going to move on to next? Oh, I see. Okay, the next thing we're going to do is a ripple tank analog of that circular tube interference experiment. Okay. Yeah, so this is... See, I think the thing about the double wall is there are certain frequencies that can sneak through, sort of resonance frequencies. So I think that might have been where we were a moment ago. Okay, so let's go to WJA3, which is constructive interference of waves in a circular tube. So this is sort of like that sound source, and then we'll have the microphone down here picking up the results. And I guess this is constructive interference. And I think it would, in principle, be possible to tweak the frequency so we get destructive interference. But in any case, you kind of see the idea that there's two paths, and that the two paths end up interfering constructively. I think if I change the frequency a little bit, you would get some destructive interference. Let's see if that works. I didn't try this in advance. Clear the waves. I don't know about that. So much for that. Here, let me try a slightly higher frequency, and then we'll move on. I don't know. Okay, I'm not convinced. WJA4 shows an incoming plane wave going through an opening in a barrier. So the angular spread in radians should be proportional to the wavelength divided by the size of the aperture, the size of the iris, or the size of the opening. So in this case, the wavelength is, probably something like 1/5 of, so here is the aperture size, and then here's the wavelength. So it appears that the aperture size is probably something like 5 wavelengths. So you get a significant amount of spreading out, but it's not gigantic. Now, if we made the frequency much larger, so the wavelength will be a lot smaller, then we should see very little spreading. So you should get a pretty good beam here. Let's see if the 3D view helps. Yeah, I think you can see it's a pretty good beam. And then, if we get down to low frequency, now it's hard even to see what the wavelength is here. But I think you can see it really spreads out, so there's no collimation at all. Let's try something a little intermediate. Okay, so you can see the wavelength is comparable now to the opening. And yeah, so that is pretty significant diffraction. So it's spreading out very widely. And if we go to kind of a little bit higher frequency, let's see if we can see a little bit of an obvious angle. I think we can kind of see an obvious angle there. Yeah, so you can see that it kind of spreads out like that. And if we go up a little more in frequency, then okay, it spreads out like that. So again, the angular spread in radians is roughly given by the wavelength divided by the opening size. And then here, let's go up even a little more in frequency. And so the higher in frequency you go, the less the waves bend around into the shadow regions. Yeah, so you see there is starting to form a pretty good collimated beam. Not too much angular spreading. And then you go up to quite high frequency, short wavelength. And I think that's pretty good. You can see it's a pretty good collimated beam. Okay, so now I have one called two sources. And I think this should look a lot like the pattern that I was trying to illustrate in the parking lot, where we had two speakers and you could walk around and you would see, as I walked around, some loud spots and some quiet spots. So I was walking around with the microphone and you could kind of see that I would go loud spot, quiet spot, loud spot, quiet spot, loud spot, quiet spot, like that. So that was the idea that we were after in that walking around the parking lot demonstration behind DRL. Oh, I guess so in past years I tried to do this in the classroom and the effect was completely ruined by reflections from the walls. And I think if I add a wall, you can see that sure enough the effect is ruined by reflections from the wall. So this never worked well in the auditorium. Here's my dog for a minute. Alfie. And then obstacle. Let's look at obstacle. Okay, so here this red thing is an obstacle, and naively you would expect that there's a shadow region in here where there, if you, for instance, if there's a sound source here and you're standing behind this wall, you might say, well, I shouldn't hear anything. And that's true for short wavelengths, for high frequencies. In fact, we can go up to very high frequency and we should get a pretty good shadow in here. And we can even look at the 3D view. And I guess, yeah, you see it's pretty quiet in this region. But then we can go down to lower frequency where diffraction is much more important, longer wavelengths compared to the size of this barrier. And we can clear the waves. And I think then we should see, yeah, so you can see that the waves fill in this shadow area much more. Yeah, so you can see that now, even though you're standing behind the wall, you hear something. The sound bends around the barrier. And I guess we could go down to even lower frequency, even longer wavelength. Whoops. Oh no, oh, that was a mistake. Okay. Setup obstacle, sorry. Okay, let's get down to very low frequency, clear the waves. I cleared the wall by accident instead of clearing the waves. And I think then we'll see This is an incredibly low frequency, very long wavelength. I think then we'll see that, yeah, see there's really, the wave is everywhere. That's kind of interesting actually. So that's a kind of ridiculously long wavelength. I think we could do something a little bit intermediate. Yeah, so here you see there really isn't much of a shadow region at all because the wavelength is comparable to, yeah, the wavelength is really comparable to the size of the wall. So that's pretty good, you see? So you can see the shadowing is like pretty much not there in the case where the wavelength is comparable to the size of the wall. So this is important for example, low frequency sounds running into maybe a column in an auditorium, or if you have a noise barrier along a highway. So if you have, like, suppose you have a busy highway here and you want to build a house over here and you put a wall in the middle, then very high frequency sound from the highway will be pretty effectively blocked, and you have a nice shadow region here where you don't have to listen to the highway noise. But if there's really low frequency highway noise, maybe the rumbling of a truck going by, then that is much more difficult to block because it will diffract around this barrier. So again, it's always much more difficult to block low frequency noise than it is to block high frequency noise for a number of different reasons. In one case, with our barrier between two rooms, partition between two rooms, it's because high frequency sounds are more easily reflected and low frequency sounds are more easily transmitted through a barrier. In this case, it's a totally different phenomenon. It's diffraction. But again, the longer wavelengths, the lower frequency components are better able to bend around the barrier. The higher frequency, shorter wavelength components bend much less, so you get a nice clean shadow region. The next one we want to do is half plane. I guess even more resembles a highway noise barrier. Let's see what half plane looks like. Oh, okay. See, so here is my noise barrier, this red line up here, and then I've got my source of highway noise over here. And I guess at this frequency, you see this barrier is much, much larger than a wavelength, and so I get a pretty good shadow zone over here, maybe where I want to build my house. So that's pretty good. It's pretty quiet over here. But now let's see what happens if we create some low frequency truck noise. So we'll go down much lower in frequency, much longer wavelength, and we'll reset the waves. And I think we'll see that it becomes less quiet over here. So now these waves are still quite a bit shorter than the wall, but I think still you see you get some wave getting through over here, bending around. And if I make the frequency even smaller, then let's see what we get. Yeah, so then you can see it's pretty hard to stop very low frequency noise. So then, yeah, the shadow is even a little less effective, and I guess we can go even to absurdly low frequency. I'm not sure what good that does. Oh, what? Oh. Yeah. Here, let's try this. Okay. The next one is called ellipse. And ellipse is like the whispering gallery problem. There was an extra credit problem. So we put a sound source at one focus of an ellipse, and then we go and listen at the other focus of the ellipse, and you'll see that you get constructive interference at this other focus. Isn't that's pretty cool? So, you emit a wave over here, and all these different reflecting paths have a length that results in constructive interference when you get to the other focus of the ellipse. So that's pretty cool, whispering gallery. And you can think about that with ray tracing, or you can, in this case, you really see what's happening with waves. Then there's another one called refraction. And this shows waves bending toward the slower medium, as described by Richard Muller in Physics and Technology for Future Presidents. So you see, that's kind of neat. So here, so here's an incoming wave, and then you can see the reflected wave is just the same angle with respect to the surface normal as the incoming wave, but then here's the refracted wave, transmitted wave, and you can see that the wave bends toward the slower medium. This is a slow medium, this is a fast medium, so it bends toward the slower medium. And then there's another one called internal reflection. And in this case, we start out inside the slow medium. And you'll see that if you start out in the slow medium, and if you strike the boundary at a glancing angle, so not like this one could escape, but one like this at a glancing angle can't escape. So at a glancing angle, it's trapped inside by total internal reflection. And that's how fiber optic cables work, and that's how the sound channels work that were a big topic of Richard Muller's Waves chapter. So this is pretty good. Yes, you see really very little gets out. So basically everything is trapped inside this slow medium because it hits the boundary at this glancing angle. And again, this has applications to whale communication, to all kinds of Richard Muller stories, to fiber optic cables for network communications. Okay, then, Doppler, okay, Doppler effect 1. So this is a moving source. And you can see that the waves move through the medium at their speed given by the medium. But you can see if you are in front of the object, you see a smaller wavelength. If you're behind the object, you see a bigger wavelength. And that's because as the wave is forming, the source is moving. So the wave that propagates in this direction has a longer wavelength. The wave that propagates in this direction has a shorter wavelength. And then the waves that propagate out in the perpendicular direction have the same wavelength they would have for the object just standing still. And if we do Doppler effect 2, let's see what that is. Oh, this is interesting. So I think in this case, we are reflecting from a moving. This is kind of complicated. What is this telling us? I think it might be telling us that the moving receiver effectively is intercepting wave fronts more often, so it effectively sees a higher frequency. I guess that's sort of the way you could look at that. Sonic boom. So if you have an object moving faster than the speed of sound, then you get this cone. It's like a wake, like a boat's wake behind the object. And I think the opening angle, there's a, let's see, a trigonometric relationship between this opening angle behind the object and the ratio of the speed to the speed of sound. Temperature gradient. Temperature gradient 2, let's see. Okay, so this shows sound traveling more slowly in cool air. The blue air is cool, and the waves bend toward the slower medium. So this is sort of like Richard Muller's stories about wave propagation near the ground with a temperature gradient. So you can see this wave, it bends toward the slower. So here's the slow medium, the fast medium, and again it bends toward the slower medium. That's pretty cool. So you've got waves emanating from here and they bend toward the slower. Temperature gradient 1 is like a temperature inversion described by Richard Muller. So I think this is where you can hear distant sounds. So here's a barrier, so no straight line propagation is possible, but you have slow here and fast here. So yeah, it's like a temperature inversion. So I think we're going to see that sound bends, it'll bend back toward the slow medium. So then you can, even though there's an obstacle in the way, I think you'll be able to hear something here. So okay, so here's sound reaching that boundary and bending toward the slower medium. Yeah, so you'll see, because of refraction, so because of the waves changing direction as the wave speed changes, because they're bending toward the slower medium, you get sound here in this distant shadow zone. So this is like being able to hear faraway sounds on a morning when there is a temperature inversion, as described by Richard Muller. And then temperature gradient 4 is like the sound channel described by Muller. So we can put, okay, here the source is outside the channel. And I think it's not too interesting. I think if the source is out here, outside the channel, then you don't have this wave trapping phenomenon. Although I guess you do have bending toward the slow. Okay, but now if we move the source so that it's inside the channel and clear the waves, I think we're going to see the waves get trapped inside the channel. Yep. Okay, that's pretty neat. So you see the wave is mostly trapped inside the channel here, because it's in the slow region. It's faster out here, and so the waves bend toward the slow, so they get trapped inside by internal reflection. And I guess temperature gradient 3 is supposed to be the opposite of a sound channel. Let's see what that looks like. So here the slow medium is on the outside, and then this middle region is a faster medium, and things bend toward the slow. And I guess if we put the source down here, we will not see any trapping. Let's see. Clear the waves. Yeah, so they escape. You don't see any trapping of waves. And then parabolic mirror 2. Let's see. Parabolic mirror 2. Is here. Okay, so I think what's cool about this is, even though this is simulating waves, you will see the waves focus in the same way as you would expect to see from ray tracing. Oh yeah, so you see here's the focus of the parabola. So you can see parallel rays come in and they're bent to be concentrated at this focus. And okay, and there's parabolic mirror 1. Let's see. Oh, I see. Okay, so now here we have a source at the focus. And the rays, see if you imagine ray tracing, the result is you get nice plane waves going out. So I guess you can sort of see why a parabolic antenna is often used to communicate with a satellite, or to send microwaves from point to point for cell phone communication between cell towers. Okay, so this is the Ripple Tank Java applet. And that's my dog. Here's a more low-tech way to show the interference between two speakers playing exactly the same tone and exact synchrony that I was illustrating in the DRL parking lot in last week's video, and that we just showed with the Ripple tank a moment ago. So in this case we have a transparency with a bunch of concentric circles. We have another identical transparency with a bunch of concentric circles, and we can put them directly on top of each other. Let's see, if we put them really perfectly on top of each other, then there's no interference pattern. You just see, you can't even tell there are two sheets. But then if we separate them a little bit, then you see the so-called moire pattern. So you can see the zone of constructive and destructive. So constructive, destructive, constructive, destructive, constructive, destructive interference. So loud, quiet, loud, quiet, loud, quiet, loud. And the pattern changes as you increase the separation. So you get more and more bands. The bands get closer together in angle as you increase the number of wavelengths apart the speakers are. So here they're, let's see, I think that's 1 or so wavelengths apart. Anyway, so that's what we were trying to do in the parking lot. We were trying to put the speakers, let's say 1 or 2 wavelengths apart, and then we were walking, and you say loud, quiet, loud, quiet, loud, quiet, loud. But it's neat that you can achieve the same effect just by overlaying 2 transparencies that have the same concentric ring of circles on them. So a nice low-tech illustration of the same concept. All right. And even one more low-tech illustration of this interference between 2 sources that are perfectly coherent with each other concept is, so this chain is black, red, and so on. Black, red, and if I move around, you can see that here I get constructive interference of black with black. Here I get constructive interference of red with red. And if I move to some other spot, over here I get destructive interference of red with black. And over here I get destructive interference of red with black, and so on. So we can, actually this is kind of neat also for looking at a diffraction pattern. So you can say, okay, I'm going to go far away, and I have 2 slits that light is passing through, and it's laser light, monochromatic light. So it's just one nice monochromatic light source, and I go out to a distant screen, and you say, okay, directly in front I see constructive interference. How far do I have to go before I see destructive interference? And the answer is you go far enough that suddenly the 2 paths are different by, well, I should have pulled it taut. But the two paths are different by half a wavelength, so then you have a crest and a trough overlapping.